Good morning. I'm Jeff Hammond with IGSHPA. Thank you for joining us for June's Dig Deeper webinar. We have a great subject this morning. I always enjoy discussions on hydronics, and we have an excellent speaker this morning. Before we get started, I have just a few slides to provide some updates on what's going on with IGSHPA and ground rules on how our webinar works. So without further ado, we will get started. Lots of news and updates. We have quite a bit going on within IGSHPA. One of the items here to keep note of is for future town halls and Dig Deeper webinar registrations, make sure you go to the events menu at igshpa.org. You'll find some new items here. Besides just the events, there's an abstract submission form for future events. If you'd like to present at a town hall or a Dig Deeper, just fill out that form and click submit, and we'll take a look at the abstract. We're always looking for new topics. Some of the other new business with IGSHPA, you'll find the business directory that was just introduced a couple of months ago. So check that out. That's it has a lot more information and filters so that you can search by products and services. We have a brand new member portal. If you haven't seen that in the e-news, that was introduced at the beginning of this month. It allows members to log in. You can change your profile, and there's just a lot of other information in there. It will continue to be built upon. And we also have a new membership option to reward those who have multiple technicians who are IGSHPA certified and have received a membership when they went through training. You can upgrade your individual memberships to a business membership. There's also the board, the job board. So you'll see a lot more in the future. Check it out on the website. Also want to remind everyone of the upcoming conference. December seems like a long way away, but it'll come before you know it. It's the week of December 5th, December 6th through the 8th is the conference and our annual general meeting. We already have some sponsors, platinum, gold, silver, and bronze. As you can see, we still have the diamond sponsor open, and quite a few of the other sponsors are still available. So get those before they're no longer available. Same with the conference exhibit hall. We have quite a few booth spaces already. There's only one 20 by 20 left. But there are quite a few 10 by 10s, and those can be made into 10 by 20s. We have a great location this year on the NGWA exhibit hall. We're just to the left of the doors. So as people come in, they're going to see the IGSHPA pavilion. We'll have a big banner above it, and you'll want to check out our IGSHPA exhibitors. Just a reminder on CEUs, we're no longer waiving CEUs for certification renewals. If you'd like credit for this Dig Deeper or town hall, make sure you send a chat message, and Sally will keep track of those and send out certificates every half CEU interval. Just some housekeeping here before we get started. If you would type your questions into the chat screen. After Michael is finished with his presentation, I will read the questions, and if we don't get to all of them, we'll do our best to reach out and make sure that your questions are answered. But we'll try to get to just as many as we can during the webinar. We're respectful of people's time, so we will stop at an hour after we start this morning and follow up with people that we didn't get to answer the questions. Please mute your microphone if you're not speaking. And also a reminder, this is being recorded, so you'll be able to find this presentation on the IGSHPA website later on. We'll probably have it online Monday, most likely. One more item before we get to our exciting topic this morning. We do have to read this disclaimer and potential conflict of interest, just so that everyone knows that this presentation represents the opinion of the presenter. It does not represent any official position, opinion, or endorsement of any products or services by IGSHPA or its members. IGSHPA town halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It's the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. All right, so now let's take a look at who we're working with this morning. Michael Ridler with Eden Energy started his career in a family-run HVAC company over 20 years ago, and that company is still in operation today. Pardon me while I move my screen back here. Michael is Technical Services Manager at Eden Energy and is responsible for mentoring and advising the technical support team at the company. He also is focused on providing field support and technical training for contractors, engineers, and builders across Ontario for heat pumps, boilers, and hydronics. Michael is passionate about learning new things and building relationships with industry stakeholders in HVAC, both new and old. Michael is first and foremost a family man who lives to set an example of positivity, mentorship, and empowering the people around him. With that, I will turn that over to Michael, and we're excited to hear the presentation. Thanks, Michael.
Thanks, Jeff. Well, obviously, I appreciate you inviting me and want to give a strong shout out to all the people that have inspired me over the last 20 years that I've been working on geothermal heat pumps, and now on the design side of trying to help put together successful systems. People like Jeff and others. Tom Kinder comes to mind, Jim Boyles comes to mind, Sean at Climate Master. There's a lot of great people that contribute to this industry. The objective today is to briefly touch on hydronic systems as they apply to water or combination equipment. We're going to cover a lot of ground in 30 minutes, so we're going to skim over a lot of stuff, but hopefully we can have some Q&A at the end of this. We're going to talk about best practices for equipment piping, but we're also going to review some of the secondary piping. And we're also going to talk about what happens when we don't focus on properly piping the equipment. This here is an illustration of a water-to-water system. So what I'm showing here, and hopefully everybody can see my mouse, this is a traditional water-to-water unit that is in turn connected to a geothermal storage tank. One of the most common things that we will see is typically tied to this geothermal storage tank. What happens is there's a little bit too many rules of thumbs, and we'll see people tying very, very small water heaters to water equipment. And in turn, not only is the buffer tank then too small, we also find that this piping that you can see that goes from the buffer tank back to that water also ends up getting inadequately sized. What ends up happening is that as the water is running and we're trying to generate that energy, because we have it under pipe and with a buffer tank that's too small, two things happen. One, we don't deliver the BTUs to the space. And two, because the buffer tank is inadequately sized, we'll end up with a situation where we have premature component failure or will negatively impact the overall performance of that piece of equipment. What I mean by that is the unit will not be allowed to run for a minimum runtime of 10 minutes. It's actually just banging on and off too quickly. In this particular case, we have a desuperheater shown that's tied to this unit as well. The tank in this case is a single tank application. So we obviously want to be conscious of, if we're doing a single tank as a desuperheater, this is not a gas-fired water heater. We do not want to be in a situation where we are drawing from the burner into the unit and causing problems. The other thing we have to be careful about is that if we are in fact going to draw off the tank, do not pull off the bottom of this tank. If we end up pulling off of that tank versus pumping the hot water into it, not only are we pulling water, we are also going to be pulling all the sediment and debris out of the bottom of this tank, and we're going to dump that into our water-to-water piece of equipment, and we will cause premature failure. Anybody who's had the distinct pleasure of replacing a desuperheater knows it can be somewhat challenging, and generally speaking, desuperheater failures are not going to be a warranty thing. We suck a metric ton of garbage off the bottom of a water heater. No manufacturer should or generally will warranty that under standard terms. The other thing you'll notice here on my secondary piping, I'm showing 3 pumps here. You'll notice that this is not reverse returned and this is not closely spaced tees. That's intentional. This piping that you see on the air separator side is actually sized so that the flow velocity is under 2 feet per second. What that means is that as these pumps come on and go off, if one pump is bigger than the other pump, this pump doesn't bully the smaller pump. These pumps will all have adequate flow going through the system. So this is a really good, simple way of piping systems to make sure that we have good flow going to all of the other zones. The only other thing I'll do is I'll come back to this geo storage tank and just point out, make sure you are dumping the hottest water into the top of this tank, and make sure your return feed is in fact going into lines with dip tubes driving that cooler water to the bottom of the system. If we were to reverse these connections and put the hottest water into the bottom of the tank, what's going to happen is we need to heat this entire tank before we can put usable heat out into the space. So this is kind of a general overview of how we would typically type or pipe a water-to-water system. Moving on, I just wanted to quickly talk about closely spaced tees. Be careful about doing closely spaced tees. So here you can see I've got closely spaced tees going out to a secondary circuit. Let's say that's a rad system. The second one you can see is also a rad. What happens is you'll end up with a temperature cascade. If I'm going out to this first pump at, let's say, 110 degrees on a 20-degree delta T, well, that means that at this point on the second pump, I'm no longer 100 degrees or 110 degrees. You'll end up with a temperature cascade, and what can happen is in the bottom right-hand pump, you could have complaints from that end user of, I don't have adequate heat because of the closely spaced T configuration. This isn't going to always occur. There's a lot of variables that come into play, but honestly, the closely spaced T setup is not something we need to be doing anymore. We have enough experience in hydronics over the last 20 years and the evolution of the math entailed in designing systems that we can get away from piping like this, and it's actually much more cost effective to pipe it using a short fat header than doing closely spaced T's, because I completely eliminate the pump that you see over here on this side. Looking at domestic hot water piping, I wanted to show a combination unit. So this is a combination unit. You can see the domestic hot water hookup. I did not draw in the hydronic tank just for space here. I wanted to illustrate a 2-tank setup. So in this case, my primary tank to the left here on the desuperheater, that tank is there just to absorb all the energy that we can. So if we looked at a 4-ton Climate Master, for example, you would probably get around 5,100 BTUs. That hot water is not being generated all of the time. We don't have a lot of control on when it's being made. We want to make sure we can dump it into a storage tank wherever possible. This secondary tank is stratified. The nice part about this 2-tank setup is you're less concerned about which elements and where the burners are, because the tank to the left is pulling all of the energy off of that combination unit. In this case, I'm showing a Synergy 3D. So the Synergy 3D capable of doing forced air heating, forced air cooling, hydronic heating, and domestic hot water. So this is a pretty tried and true method of piping it. The only disadvantage of piping in a 2-tank application, which many of you will know already, is it does add to cost having that second tank. So always keep that in mind anytime we're doing any sort of a design. I wanted to touch on PEX on equipment. Big proponent for PEX. We use PEX in a lot of our systems. I am not saying don't use PEX. Just be conscious of what PEX you are using. I've heard the statement over the years, PEX is PEX. That's not valid. Lance McNevin from PPI is an absolute expert on PEX. If you have time to talk to Lance, take advantage of it. PEX A, PEX B, and PEX C have a completely different manufacturing process. And what that means is the temperature burst rating is not the same across different types of PEX. You do not want to run PEX directly to a compressor bearing unit, because if it has an integrated pump, what will happen is if that pump fails, it will flash to steam and it can result in your PEX bursting. And I have an illustration of that here where a contractor has run PEX directly to the unit. The pump is seized, it flashed to steam, and obviously the PEX is not designed to run steam through it, and you can end up having a rupture. So what we like to see is that between the unit and the storage tank, run that in copper or PPR or something similar. And then on the secondary side, if you want to do a copper header and then run PEX from there, it's good practice. This doesn't happen a whole lot, but all it needs to do is happen once and you end up with an insurance claim that you really don't want to deal with. The other thing that's really important, we talked about it earlier, is buffer tank sizing. We're still seeing occasionally where people are using traditional water heaters and hooking them up to a system. The challenge of the buffer tank is if you have a 4-ton piece of equipment and you have a radiant floor system that is zoned, you can be putting out 48,000 BTUs off the piece of equipment, but you only have 5,000 BTUs going into a particular zone. We need a place for that additional energy to go, which is what the purpose of the buffer tank is for. So in this case, if I look at this and say I've got 48,000 BTUs on the equipment and I have a 5,000 BTU draw, I'm allowing my tank to shift down 10 degrees. This clearly shows us we need over 90 gallons of storage in order to achieve that. So we have to be very conscious of making sure our buffer tanks are sized appropriately. If we don't size them appropriately, we're going to end up with premature component failure, and we're also going to end up with comfort issues. On top of that, we're not going to allow that compressor to reach its steady state, and we're going to negatively impact the efficiency of the equipment. Number one thing we're selling here is comfort. So obviously we want things to work great. But the other thing we're doing is we're selling efficiency, and little things like not putting the right size buffer tank in and not sizing piping properly will negatively impact that. I've thrown an example in of a buffer tank. Our company, Eden Energy, offers a whole whack of different buffer tanks as we design systems. I just wanted to illustrate this to point out that there are a lot of new tanks that have come to the market. This particular tank, which is an Argosys tank, and again, I'm not trying to push Argosys on anybody. I just want you to see this is a heated and chilled tank that also acts as your hydraulic separator. The other nice part about this tank is it's a fully composite tank. So it actually has a higher temperature pressure rating than a steel tank does, but better yet, a 120-gallon tank, Jeff or I can carry it around by ourselves. Those of you who've been in the field like myself know that 120-gallon tanks traditionally is not being carried around by Mike himself. So there's a lot of cool technology out there. Don't be afraid to look at new tanks or new applications, but obviously, lean on IGSHPA and lean on people on your own team to make sure you're applying the technology properly. The other thing we see a lot is pipe sizing on heat pumps. We actually have a video on our YouTube channel where Max Rohr, Bob Rohr, and myself did about a 1-hour presentation. And what it's called is heat pumps are not boilers. And we specifically went through the piping of it. We are seeing where units are still getting piped with pipe sizing that is just too small. So what I mean by that is people will go out, they'll put a 5-ton water-to-water unit in, they'll pipe it with 3/4-inch piping, because in a boiler application, you're well within that 2 to 3 feet per second. The thing that's being missed is that on a geothermal water-to-water piece of equipment, we need 2.5 to 3 gallons per minute per ton to actually be able to ensure adequate flow through the unit. So if we look at that, I've done 2 side-by-side comparisons. I've done an IBC boiler on the left, where 1 gallon a minute is 10,000 BTUs. And again, the way we get that is 1 gallon a minute times 500, which is my constant for pure water, times my 20-degree delta T. So if we looked at 65,000 BTUs, that's 6.5 gallons a minute. As I'm sizing the pipe for part of a design, 1-inch pipe, 6.5 gallons a minute. On copper pipe, I'm 2.5 feet per second. I'm happy. I'm not going to have any issues with that. If I take that to a water-to-water and say 2.5 gallons a minute is 10,000 BTUs, there's a reason for that. 2.5 gallons a minute, I've picked the minimum intentionally, times 500 times the 8-degree delta T on the equipment, that's 10,000. So if you look at 65,000, we're now at 16.25 gallons a minute. If I pipe that in 1 inch, I have now exceeded that 2 to 3 feet per second. I'm now in a situation where I'm going to have problems with that unit. We need to make sure we get all the BTUs off the equipment into the buffer tank or into the loads as they're needed. Again, just looking at some examples here, I picked a couple of water furnace examples since I know that product quite well. If I look at what they are saying in their own manual on an NSW 060 at 3 feet per second on 1.5 inch piping, the other thing on the right-hand side is you can see I can easily pump that. So if the equipment has an integrated pump that's designed to move 18 gallons a minute at 12 to 15 feet ahead, we're great. Well, what happens if I don't pipe it the way water furnace is saying? I don't do 1.5 inches, I do 1 inch. On the bottom, you can see my flow velocity starts to creep up significantly. I'm over 7 feet per second, but on top of that, I've introduced a significant pressure drop, which makes it difficult to pump. Good news is we don't have to think about this. Enertech, ClimateMaster, Water Furnace, Bosch, all the major players, inside their installation manuals, they have a chart that looks like this. It will list all of the equipment. It will list the copper pipe size. Pay attention to the copper part. PEX, a 3/4 inch piece of PEX is not the equivalent to a 3/4 inch piece of copper. They have a different dimensional ratio on the thickness of that pipe. So here where they're saying 1.25 inch, they're specifying their flow rates. They're making some recommendations on maximum size. And on the right-hand side, they're also indicating the proper size of the buffer tank. So obviously we want to make sure we're always following manufacturer's guidelines. If we deviate from the manufacturer's guidelines, we start to introduce a warranty problem that we don't want to deal with. What happens if we don't size our pipe or our buffer tanks properly? The number one thing is noise. The equipment is going to sound a lot louder than it should be, and it makes a lot of sense. If I'm generating 120-degree water and I'm not moving that water off the vapor refrigerant system, that unit is going to drive the head pressures up, the temperatures are going to go up, and I'm going to end up in a lockout condition. So we'll have head pressure lockouts, we'll have complaints of not enough hydronic heating, not enough hot water. We'll also have performance and comfort issues. And what I mean by that is if you've installed a water-to-water and you're expecting it a COP of 3, you might be getting a COP of 1.5 because we didn't size the buffer tank properly or put the system together properly. You can have other little component failures, boards, capacitors, compressors. The biggest thing that happens is you have a really irritated homeowner and you get that loss of repeat business and that faith in you. One of the most common comments I will hear on this is, I put that water to water in, I underpiped it, I put a different buffer tank on it, and I didn't hear about it. The reality is I might not have heard about it because they may have called Jeff Hammond to get him to fix it. The fact I didn't do it right and nobody told me doesn't make it right. It's a distinction between units that are running and units that are working properly. If we look at how we're designing systems, this is a really good diagram that I pulled out of the Climate Master Hydronic Applications Manual. It's a great book to read. It's really important that we pay attention to the difference between our source and our load temperature. Don't instinctively design your system so that you're putting out 120-degree water if you don't in fact need 120-degree water. As we increase the difference between the source and the load temperature, we are decreasing our overall performance of that equipment. So a great example of this is a photo that I got from Curtis Boyd at Nottawasaga Mechanical. And so in this case, you can see that on the top left-hand corner, the supply temperature is 120 degrees. And the reason it's 120 degrees is because the system was designed with 12-inch tubing. So the spacing on the tubing is 12 inches inside of that floor. For a couple of $100 up front, we changed that around so that it would be on 6-inch spacing. And on 6-inch spacing, we've actually reduced the water temperature required to heat that space to under 110 degrees. So really what this is saying is you can pay up front as part of your design of the system to put a couple $100 of extra tubing into the floor, and what that means to the homeowner over the life of this system. This is not a change that we can make later. If we look at a COP performance table, you can see here that with a 30-degree source and 120-degree entering load, we got a COP at 2.5. As we reduce that entering load water temperature, our COP dramatically increases. Just by putting a little bit more tubing into the floor, we can take our efficiency from 2.5 to 3.4. And as we all know, when we're talking about a COP number, we're saying for every unit of energy we pay for, we get 3.4 for free, or we get 2.5 for free. You can actually get into a situation where you can push the COP to 4.5. And the way that we do that again is by controlling the entering load water temperature. To do this, you pay a little bit more upfront, but I am the proponent for, I would rather pay a little bit more money upfront to have a properly designed system and utilize newer technologies so that I can make this be a really efficient system. This photo here is from my own house. So what is in this place here? I heated my house with 98-degree water. So this is what's called ROW panel. This is a heavy gauge extruded aluminum. I laid it down on the floor in one of my rooms that was not properly heated. And the overall efficiency of this system is phenomenal. Again, you can see I've got the water temperature so low that I know I've got a COP in excess of 3 at all times. When I don't need that full 98-degree water, the outdoor reset actually creeps me back to 80 degrees. And at that point, I can have a COP that's in excess of 4. So this isn't really new technology. It's newish technology, but this is the kind of stuff you can use versus doing traditional tubing in the floor. Other things that you can look at is you can look at things like convectors. So in this case, I borrowed this photo from Yaga. This is a low H2O convector. On the left-hand side, you can see they typically get installed along outside glass in the building or in front of a sliding door. So you'll see this in a lot of MERB buildings. You'll see this in higher end homes where architects are designing these beautiful homes. The point of this is that these, again, will produce usable heat with water that's less than 100 degrees. These units you can see right here from my mouse, it's a fan assisted unit. So these units use less power than your TV turned off in standby mode, but they deliver a lot of BTUs at a really low water temperature. This is going to be more money than a traditional rad, whether it's a Yaga or another brand. But again, you pay a little bit more upfront, and for the life of the system, you're paying less, which becomes more and more important. And that's it, Jeff. I have gone through my presentation to try to honor everybody's time here. Obviously, we have much longer versions of these videos. We actually have videos that are 6 or 7 hours long, talking about piping systems, talking about heat pumps, talking about boilers. If you look up Eden Energy Equipment on YouTube, LinkedIn, or Instagram, I've put my information, including my phone number and extension and email at the bottom. I'm happy to work with Jeff. I'm happy to work with IGSHPA and be involved. And people, I encourage you to reach out to either one of us if you have any comments.
Thank you so much, Michael. I'm going to check the chat and see what questions we have. We have plenty of time for questions, so please submit your questions in the chat room. Also, if you're looking for CEUs, please make sure you send a message in chat. So our first question is from Arlene. She asks, can you repeat the name of the last two flooring technologies?
Yeah, so I'll go back a couple of slides, and I know I was going quickly. On our YouTube channel, we have an in-depth deep dive on this product. I just wanted to sort of skim over some things, and obviously anybody can email me or call me at that number. This product is called RAU panel, so RAU panel. So this system is quite unique. It will produce 28 BTUs per square foot at 110 degree water. So in my own home, I didn't need 28 BTUs per square foot. I actually have doors that have doors in them. They're not open to the outdoors. The numbers that I'm giving you are not the manufacturer's numbers. The numbers that I'm giving you are independent numbers from Virginia Tech University, which is important. Not that manufacturers mislead on numbers, but we always want to know the source of the data. So this is called RAU panel. Another option that you could look at would be like an Uponor warm board product, a Rayhow RAU board product, and Roth also makes a paneling system. And as I say, if you reach out after, I'm happy to share more on that. This system is called YAGA. It's called a low H2O convector. This one is in the floor, but there are also ones that go on the wall, just like a traditional panel rad. And there's also ones that can be hidden inside of the wall, so you physically don't see them, called a Brisa. But again, there's lots of different brands. I just picked brands I'm very comfortable to speak to. But if you do a little bit of research, you can find a lot of them.
Great question. And I appreciate the answer, Michael. The next question is from Rick. He would ask you to speak on the issue of dirt in the floor embedded radiant unit.
Yeah, that is a great comment. And I was hoping we'd get some awesome questions. So I'm going to go back a few slides. So right here, you'll notice on my drawing, I'm showing a dirt separator. There's a reason for that. I prefer Cleffy myself, but there's a bunch of different varieties there. Just to be clear, I prefer Cleffy because Bob and Max Rohr are friends of mine, and we work with our friends just like Jeff and I work together. The point of this dirt separator is to make sure that whatever is in this tank or in this radiant floor system does not get stuck inside of the heat exchanger in the piece of equipment. I always make the joke when I'm doing my all-day hydronics training, if you forget the dirt separator, don't worry. You do have a filter, it's the pump. So if you're having premature pump failure, it's because you don't have dirt separation. One of the things to really keep in mind is there's a lot of ferrous material inside of our water. And pumps nowadays are becoming more and more ECM. There's less and less non-ECM circulators being used, and they're magnetic. So what ends up happening is that ferrous material gets attracted to that pump, and it can cause that pump to fail. There are pumps on the market that can handle that very well. A great example of that would be the Taco 0015 or 0018 series. They actually have a design inside of their pumps where they have a bio barrier. So it tries to keep the material away from the pump. But the point of the dirt separation is to protect the appliance itself, whether it's a boiler or a water to water, and it's always installed on the return side of the system. Just continuing on that point, the other thing to note here is my air separator. Air separators do not go at the highest point. I spent a lot of time in the field installing systems. I thought they went at the highest point. It is absolutely wrong. What happens is we flush out all the air using air vents, but the system itself, when we fill it with 65 degree water, we've got over 3% air that's actually entrained in the system. The way that air comes out is when we heat the water. So when we put a pot on the stove and we boil that water, that air is coming out. Well, in our system, we need a place for it to come out. So the air separator always goes at the hottest point, not the highest point.
Excellent. All right. Here, the next question from Rick. How does cost of those floor radiant approaches compare, including light cast, gypcrete?
Oh, that's a great question. So the RAU panel system, I'm just going to keep jumping slides so we can all see. This RAU panel system, again, I'm in Ontario, so take everything I say with a grain of salt. Up front, it's probably going to be in the 20 to 35% more than doing a gypcrete system. But there's a couple of things to keep in mind. Number one, you don't have construction delays. The construction delays are you're bringing in somebody else to pour gypcrete, and now you've got a week where you can't be there. You have no control over the job. So what I like to tell people is don't charge this RAU panel out at some exorbitant markup because it's additional material that you wouldn't normally be selling, but also make sure when you make the comparison, you are including the cost for work that you wouldn't be doing. This is the RAU panel option. The RAU board option is much closer in line to gypcrete because it's a wood material. And as I say, anybody who reaches out to me afterwards or reaches out to Jeff, I can send more details on the ROW panel and the ROW board product. So it's a little bit more money up front. The big distinction, again, as we go back to this slide, is the COP. We've taken that 2.5 COP. In the case of mine, I'm actually at 98 degree entering water on my, or pardon me, leaving water on my system. So you can see I'm somewhere between a 3.4 and a 4.5 COP versus the guy doing gypcrete, and I'm not knocking it. We do a lot of systems that way. It's a big difference in the COP.
Thank you, Michael. Make sure everyone's checking the chat. Lance McNevin of PPI has made some really good comments in the chat window and has a link to PPI's TN17 document, which talks about PEX and Michael's earlier comments. So appreciate that, Lance. Rick asks maybe to speak about room dirt that can get into the floor air part as well. Does it have an air filter that can be cleaned? I think that's the Yaga device that he's referring to.
So again, not trying to be the Yaga poster boy here, but this is a really cool technology, and I try to gravitate towards really cool technology. So if you look at the grill on this, there's a few things they've done. They've designed this grill so that no large debris can get inside the system. Yaga is so detail oriented that they redesigned this cover, which comes in any color you want, whether it's wood or a painted finish, because in Europe, women wear different high heels than apparently women in North America. So that's how detailed they are. They redesigned this grill so that high heels in the United States and Canada wouldn't go through them. Looking inside of the unit, this is a blowout that I've included. So this component right here is the heat exchanger, and this is the fan itself. There actually is no line voltage inside of this unit, so there's no concerns about electrical or any sort of dust getting inside of the system. This is actually a flexible grill. You can't tell by looking at it, but you can literally just flex the grill off of the system and you just vacuum it out. So no concerns from a standpoint of like water getting in from a door or any sort of dirt here. If somebody was to actually sweep the floor and try to put a large amount of debris inside this unit, this grill will stop that from happening.
Excellent. All right. Carl asks if you could comment on using fewer boreholes, but going deeper for heat transfer, 200 feet per ton for residential heating, cooling. I guess we're on the source side here rather than the hydronic side, but with your experience, maybe you can comment on that, Michael.
Throw it at me one more time.
Could you comment on using fewer boreholes, but going deeper for heat transfer?
Well, so everything's a little bit different. That's a loaded question, as Jeff will know. If you can go deeper and still make it be cost effective, then I would never knock it. So for example, my own home, I've got a postage stamp front yard, and Jeff and I were hanging out this week and I was trying to figure out how am I going to put a loop in my front yard. And to your point, I'm going to achieve it by going deeper. So you would have to do some surveying of soil conditions, which we know already, to figure out, okay, what is there and how long does that loop need to be? As a general statement, I don't base my loop design based off the piece of equipment. I don't believe that I'm going to be able to drill deep enough where my entering water temperature in the wintertime goes from 32 degrees, speaking for Ontario, to 50 degrees. So you want to design your loop with a focus on cost of that. And I would honestly be more focused on making sure you have a properly designed ground loop and making sure that all your indoor load side piping gets tweaked, because there's some big gains to have there, as you can see. I didn't change the source temperature in any of those discussions, but I pushed the COP up by over 100%.
A really good point. Yeah, the load side temperature has a big impact. Steve asks, what's the reason for not using a reverse return on the distribution side of the hydronic system?
Yeah, that's a common one. I'm going to go back here really quickly. So right here, typically why people do reverse return, and there's absolutely nothing wrong with it, is if we reverse return this, and I probably should have had a slide to show it, but with reverse return, it just means we have better even flow through the system. It's sort of like the closely spaced T conversation. Why are you not doing closely spaced Ts? This is a very simple system that achieves the same thing. So this piping right here, and hopefully everybody can see my mouse where the air separator is. In my photo, it all looks like it's the same size, which is a bit tricky. But this piping right here, I've sized it for under 2 feet per second. And by doing so, I've achieved the same as I have done with a reverse return. At under 2 feet per second, these pumps, when they run, cannot see each other. So if this is the biggest pump and these two are small pumps, this big guy running, if it's not reverse return and all this tubing's the same size, this one's going to take all the BTUs. Or If they're all the same size and this one has shorter piping on it, same thing's going to happen. So closely spaced tees, reverse return is how we get around it. That's more expensive than doing the short fat header configuration. If you go on our YouTube channel, we have an entire series of videos where we talk about this in detail. And in fact, the YouTube video where I talk about heat pumps are not boilers, I live drew 3 systems in CAD and there's a lot of dialogue. So hopefully that answers it, but it's hard to cover with this one slide.
Great. Speaking of boilers, Tom asks about the significance of design of the floor. If it was a retrofit in particular, if you have insufficient perimeter and backing insulation, thermal breaks, what happens with a heat pump system versus a boiler?
Well, it's the biggest disadvantage, and we see this a lot in design, is that if I design a boiler system, which we do, I mean, we're heat pump guys, but we do still see boilers. If I design a boiler system and the existing piping is not up to snuff in the floor, the way that we get around it is we turn the boiler temperature up, right? So if I design it for 120 degrees and it's not heating properly, it's not right and it's not efficient, we turn the water temperature up. Now we run it at 140 or 150. And honestly, that's a mistake we see on heat pumps. They turn the water temperature up, not recognizing that if you have a leaving water temperature of 130 degrees on a water-to-water unit, you're going to kill that unit. You've pushed your head pressure up over 590 PSI, and with a 600 cutoff, you're in danger land. So what we do, and again, ironically covered in the same YouTube video I'm talking about, not to push YouTube, we will actually use a small boiler injected into the system so that those 3 or 4 days out of the year where we might need it, that boiler turns on. The key is that boiler cannot see this water to water. It needs to be piped in a very specific way, because otherwise that boiler, whether it's gas or electric, is going to cause, again, catastrophic failure. So in that situation, I would do a 2-stage system. Stage 1 is my water to water. Stage 2 could be an electric boiler or a gas boiler, depending on what the requirement is. And as I say, there's drawings on our YouTube channel and part of the videos. And if you reach out to me, I would happily share some of those mechanical drawings as well.
Excellent. Thank you very much. While we're waiting for some more chat questions, I'll throw in a couple that I had prepared here in advance, if you don't mind.
Yeah, no problem.
Can you talk a little bit on the difference, at least in your opinion, between using multiple pumps for the individual zones versus a central variable speed pump and zone valves?
Yeah, that's a great comment. So what Jeff's saying is, in this air separator, I would have a pump right here, and then I would have a bunch of zone valves instead. So that's a great way of doing things. If you look at everything from a standpoint of how many BTUs per watt are you getting, which is a huge thing. If I do these 3 pumps instead of 3 zone valves, I might get 900 BTUs per watt. If I decided to do this with zone valves instead, I can probably get in the range of 3,000 BTUs per watt. So again, it comes back to that discussion of overall system efficiency. Cost-wise, it's going to be very similar. The only downside of me doing all of these in zone valves is I think of it from a service install standpoint. If this is the main floor, if this is the first floor, and this is the second floor, if I use pumps and I lose the one pump, I lose the whole house. So you want to try to plan around, where is my redundancy? The fun part is that these days, Grundfos, Taco, and Velo all make ECM pumps that are so efficient that the difference in cost between a zone valve and a pump, it's not like you're adding $100 to their hydro bill every month. Every system has to be designed accordingly, but a system with 3 zone valves and 1 system pump would be a great way to do it, and I would do that in my own house.
Very good. Thank you. Next question. Which one handles partial loads better, individual pumps or a variable speed pump with zone valves? Kevin asks that question.
So we don't sell any non-ECM pumps on our systems here. I'm in Ontario, Canada. As I say, I can't speak for outside of Ontario, Canada. So that ECM pump, my favorite to use would be what's called the 0015, which is a Taco product. That pump actually has a dial setting for zone valves. There's no requirement for a differential bypass or having to think about how to set it up. The 0018 version of that pump actually has the ability to me to connect to that pump with Bluetooth on my phone. Don't be intimidated by that. And I can see where it's running on the curve and I can change it. So I'm not really too concerned either way. With the pumps that are available now, whether it's Taco or Velo or Grundfos, all three brands are great. They're all going to get the job done, I guess is what I'm saying.
Very good. All right. Another question while we're waiting on some more chat questions here. You're showing an air separator and a dirt separator in this drawing. What about a combination air and dirt separator instead of the two devices?
Yeah, that's a good comment. So there's a variety of different manufacturers that make both. The reason I like Caleffi is Caleffi does a lot of research. They put, and I'm not saying other manufacturers don't. So I was in a scenario where I needed a combination air and dirt separator. So I reached out to Caleffi's engineering team many years ago, and they were able to confirm that the air separator is still going to work really good on the return side of the system. The reason that's important to me is the dirt separator always goes on the return side of the system. So if you're going to do a combination one, it's not going to be over here. If it's over here, that means that all the dirt and sediment sucked out of this tank is still going back into my appliance, whether it's a water to water or a boiler. So nothing wrong with a combination one. You can put it on the return side. A combination air and dirt will be more money for one unit, but it's still less money than two individual units. And for us installers, it's easy to put one thing in than two. So it will save you labor. Generally, I only do it where I'm tight on space. If I can do a proper separate air and dirt, that is my preference.
Very good. Well, excellent questions today. I really appreciate everyone's participation, and thank you so much, Michael, for your time today. As I mentioned, this recording will be on YouTube. If you go to the IGSHPA.org website and look for the YouTube icon at the very top of the page, you'll be able to find this video. It will likely be online in just a few days. So probably by Monday, it will be online and ready to watch. Feel free to reach out if you have any questions. And I hope you have a great weekend. Thank you very much for your time. Thanks again, Michael.
Thanks, Jeff. Thank you, everybody.